Hi, I'm Paul Bunn, and I'm going to be presenting our work on efficient three-party distributed ORAM and DPF protocols, which is joint work with Jonathan Katz, Eyal Kushilevitz, and Rafail Ostrovsky. I'll start by giving some background on cryptographic protocols that are relevant to our work, including ORAM, distributed ORAM, FSS, and DPF, and then I'll dive into our results and talk about our different constructions for three-party DPF and three-party ORAM. And then I'll conclude with some future directions. Before describing all the relevant cryptographic protocols that will be important to this work, let me give a highlight of our results. So we have two results in this work: a three-party distributed point function protocol, which is secure against two semi-honest corruptions, has root-n complexity in terms of communication and computation. While our three-party DPF protocol is not asymptotically superior, we believe that it's a simpler protocol, and as such, there are concrete efficiency gains, and it's easier to use and extend to other applications, which we show in our second construction in three-party DORAM. Our three-party DORAM protocol tolerates a single semi-honest corruption, has root-n communication and linear computation per DORAM operation. While these numbers asymptotically are inferior to other known DORAM results, Donor and Shalat showed in 2017 that linear computation protocols could actually outperform asymptotically superior ones, and indeed to such an extent that they open up new realms of feasibility in terms of the size of memory that can reasonably be handled. Our work is similar to that of Donor and Shalat, except in the three-party setting, where we attempt to further optimize efficiency and overall running time by using black box use only of cryptographic primitives, have small constants, and even though it's linear operations, all of these operations are local and fast, like XOR. Okay, so let me talk about the relevant cryptographic protocols. So ORAM, there's a client and a memory which we view as an array of data values, and the client has a list of instructions of reads and writes that he wants to perform on this database. The obliviousness property means that the server should not learn the read position or write position I or the write value V. And this includes attacks against timing in terms of how long an operation takes, or repetition if the same position is read multiple times. Also, the server should not be able to distinguish between a read versus a write operation. And finally, we note that there's no security requirement for the client. The client knows the positions that he's reading and the values that he's writing to. ORAM has strong connections to private information retrieval and writing. So in private information retrieval, a client is able to access an unknown element in an array held by the server so that the client learns the value held at position I, but the server doesn't learn which position is read by the client. Private information writing is defined similarly, except now the client has a secret position and a write value that gets written to the remote database, such that the database doesn't learn the secret position or the value being written. While ORAM is concerned about obliviousness for the server, distributed ORAM or DORAM is concerned about security, additional security for the client. In this case, we don't want the client to learn the read position and write position or the write value. So instead, for distributed ORAM, the client is distributed between two or more parties. And I'll note that distributed ORAM is not the same thing as multi-server ORAM. In multi-server ORAM, the server is replicated and there's multiple servers that a client interacts with. In distributed ORAM, the client is simulated by many parties, each of which should not learn the secret read and write position or value. In recent years, DORAM has become a well-studied cryptographic primitive because of its applications in MPC and the RAM model of computation, whereby you want to run a RAM program where M parties are doing the computations of the reads and the writes, and none of them are learning the values being read and written to. By starting with an ORAM protocol, this can be transformed in a generic way to a DORAM protocol by using generic MPC to simulate the client. However, this generic approach of getting DORAM from ORAM is expensive in practice, and in recent years there have been a number of works that have addressed the DORAM problem directly, looking for more efficient solutions. The next cryptographic protocol that's relevant to our work is function secret sharing, or FSS. So FSS takes a familiar notion in crypto of secret sharing a value and extends this to secret sharing a function, whereby a succinct encoding of the function is given between two or more remote servers. Then for an arbitrary function input, the servers are able to evaluate that input using their encoded share. Then function secret sharing also provides a reconstruction phase whereby these shares are combined to get the final output of the function. Concretely, a function secret sharing scheme consists of three protocols: gen, eval, and reconstruction. The gen protocol takes the security parameter and the function as input and outputs keys to each party. The eval protocol dictates how a party can use their key to get an output share for f of x. Finally, the reconstruction protocol describes how the parties can combine their shares to form the final output, which matches the original function applied to the value x. Efficient FSS protocols are not known for any arbitrary function, but rather specific protocols have been designed for different classes of functions. To date, the most useful instantiation of FSS applies to distributed point functions, or DPF. A point function is defined to be identically zero on its domain, except at one index I where it has value v. For example, a distributed point function construction implies PIR as follows. So imagine a client who will act as the DPF dealer has a secret position I that he wishes to read from a database. If we replicate the database between two identical servers, the client can act as a DPF dealer for the DPF function with secret position I and secret value 1. He deals the keys to the two servers, and they evaluate every point in the domain, the top server getting Boolean vector of length n, where n is the size of the database. His shares are A, and the second server gets the identical thing with shares of B. And FSS has the property that these two shares, when you reconstruct them, they will evaluate to 0 everywhere except at the secret index I, where they evaluate to 1. So if each server calls evaluation at every point, eval all, and applies that Boolean vector that they get, and applies a dot product to their values in their database, notice that all values will cancel except for in the secret position where you will get back the value. The clients then return their shares of this dot product to the client, who can recombine them and read the value in position I. Distributed point functions can also be used to imply private information writing. This is a similar case, except that databases are a little bit different. In the previous example for PIR, the databases were identical. In this example, the two or more databases will have different shares, with the property that the shares XOR to the actual values held in the database. In this application, if a client wants to write value v in position I, he will run the DPF protocol on these two inputs for this function and distribute keys to the two servers. Again, the two servers can evaluate at every point, and notice that the shares of these evaluations are 0 everywhere except for v in the secret position. So if they simply add their shares of the eval all vector to their own database, the virtual database, which is an XOR sharing of the two servers' databases, will be exactly updated by 0 in every coordinate except in the desired coordinate I, where the value v has been updated. Some points I want to emphasize about both these constructions. So first is that they both involve very low communication between the client and the servers, and require no communication between the servers and each other. And this is a direct byproduct of the known 2- and 3-party DPF constructions in terms of cost of dealing the gen keys to the servers. However, both servers must evaluate the FSS keys on every evaluation point in the domain, which means computation, each server must locally do linear computation. The point of emphasis here, though, is that all the computations are cheap, XORs, and they're all local. The other point I want to make is that the construction of PIR and PIW, even though they both use a DPF scheme, the server model is very different. For PIR, the servers are holding identical shares, which is the exact values in the database. In the PIW model, they are only holding secret shares, like XOR sharing of the data. And so therefore, if you want to build an ORAM protocol using PIW and PIR combined, you would need to reconcile these two different ways in which the servers are storing the data. Okay, with the background information on the different cryptographic primitives, let me again summarize our results. So first we construct a three-party distributed point function protocol that's secure against two semi-honest corruptions. Our protocol has root-end communication and computation complexity, which matches known complexities of other results, but we believe there to be concrete efficiency gains, as well as having the advantage of being easier to use and extensible. And as a demonstration of this, we present a three-party ORAM protocol that tolerates a single semi-honest corruption, has root-end communication and linear computation, but is concretely very efficient because of its black box use of cryptographic primitives, small constants, and the linear operations are local and fast. Okay, so let me turn now to our two concrete constructions, starting with our three-party distributed point function construction. So first, why do we study three-party case? Well, in some settings, three parties may be what you naturally have. With an eye towards the final application of using distributed point functions to construct an ORAM protocol, let's compare and contrast the different constructions of DPF for the different number of parties. So for the two-party distributed point function, the GEN protocol is very efficient in terms of the communication costs of dealing the keys to the different parties. It's logarithmic in the size of the database. Unfortunately, using FSS, two-party FSS as a building block for ORAM, again, we have the different models of the servers where for PIR and using FSS, you have a two-server model where the servers hold identical databases. But for PIW, they hold shares of the database. So if you have a general ORAM protocol that needs reads and writes, how do you reconcile these databases that have different data and get updated differently? In the three-party case, three-party distributed point functions are asymptotically inferior in terms of the communication cost of dealing the GEN keys. However, an advantage of the three-party case is that it's easy to reconcile this PIR versus PIW issue with the servers holding in one model the same shares and in another model different shares of the data. Also, for our specific DPF construction that I'm about to show, there is a black box reduction of the client into the distributed model, which is another advantage of the three-party case. Another thing to observe is that even though the communication of the dealer is root N, all FSS-based constructions of PIR and PIW, and therefore of ORAM, require linear work of the servers. And therefore, if the communication network is reasonable, the linear work might actually be the bottleneck. And the higher cost of communication in the GEN protocol between the three-party case versus the two-party case may be irrelevant. To give a high-level intuition of our three-party DPF construction, let's start with a warm-up example of a linear solution. So on the right, I have the database imagined as an array, and I've segmented it into blocks of size lambda, where lambda is the number of bits in the value that we want to represent in our DPF function, v. Here, the secret position is I, and so the ith set of lambda bits. In the end, the servers should be sharing something that XORs to v in position I and XORs to 0 everywhere else. So in the warm-up solution, which will be a linear solution in terms of communication for the GEN protocol, the dealer will deal keys to each player so that the keys have an overlapping property in all the off coordinates that aren't equal to I, and have a separate property in coordinate I where the keys add up to the secret value v. So for example, in the first entry when j is 1, the dealer would deal keys A1 and B1 to the first player, B1 and C1 to the second player, and C1 and A1 to the third player. Notice that if the three players were to XOR their values together and then combine them in the reconstruction phase, XORing everything together, because each key appears exactly twice, the A's cancel, the B's cancel, and the C's cancel, you get exactly 0 in all the off coordinates j. Meanwhile, in the on coordinate, A, B, and C all appear exactly once, D appears 3 times, 2 of them cancel, and you get just A XOR B, XOR C, XOR D, and the dealer selects this to add up to the secret value v. So this solution is correct, and it also enjoys 2 out of 3 security, because if you notice, if you look at any two players' sets of keys, exactly one of their keys will match and the other one will be different. This is true both of the secret position I as well as all the off coordinates. There's exactly one overlapping value and one that doesn't match. Our actual construction follows the spirit of the linear solution, except that now, instead of dealing a linear number of seeds, we will deal a smaller number, and then we'll expand these via PRG into bigger blocks. One key observation here is because of the nature of the overlapping keys, when we apply a PRG to each one of them, they will still cancel. Therefore, in all non-secret positions J, the PRG applied to the seeds when we reconstruct will cancel everywhere and we'll get 0. That has the desired correctness property. The hiccup is in position I. Now we cannot choose seeds such that when we apply a PRG to them, we get exactly the value V we want. So instead, the solution is to deal what's called a correction word, where we can correct the PRG applied to the 4 seeds by the desired delta to get the desired valued V. There's some subtle issue here of how to get the correction word to only apply to the ith block and not to all the other positions. This also leads to the square root of n asymptotics in our solution. You can ask how many seeds should we deal and how big is the correction word. And these two parameters pull you in opposite directions. So on the one hand, the more blocks you have, the more seeds you need to deal, and we want to minimize that number. On the other hand, the fewer blocks, the bigger the correction word needs to be dealt. And so the optimal solution is making both of these things meet in the middle at root n. I'll now describe how we can take our 3-party DPF protocol and extend it to a 3-party ORAM construction. So recall from earlier that there's a straightforward extension of DPF to PIR and PIW, which collectively give you an ORAM protocol. However, taking ORAM and extending to DORAM is expensive if you use generic MPC techniques. Instead, what I'd like to do is leverage the simplicity of our 3-party DPF construction to give a direct way to distribute the client. And recall that distributing the client means that no single party should know the secret position or the secret value being read or written to. Instead, this position and value should be shared amongst the different parties, in our case, the 3 parties. The takeaway point here is in how we achieve correctness in our DPF construction, which is namely to deal these seeds in this overlapping way so that they cancel in all the off block coordinates. But meanwhile, in the on block coordinate, they each have a common seed that's common to all 3 of them, and otherwise A, B, and C are distinct. So because these seeds are random, they don't satisfy any certain property other than the overlapping property. This allows us to have the parties generate the seeds just by using black box crypto, oblivious transfer, to generate the seeds with the appropriate overlapping properties so that you have cancellation in all the off block coordinates and non-cancellation in the secret block. I'd like to conclude with directions for future work. So in this work, we demonstrated the 3-party function secret sharing scheme for distributed point functions that requires quadratic communication between the dealer and the servers as part of the GEN protocol. In the 2-party setting, there are known constructions that require logarithmic communication between the dealer and the servers for the GEN protocol. There remains an open question of how to construct a 2 out of 3 secure protocol against a semi-honest adversary in which communication drops below root n and potentially all the way down to logarithmic. Also, while back-of-the-envelope computation suggests that our 3-party ORAM protocol may be concretely more efficient than alternatives out there, we plan to implement and benchmark our solution and answer the key questions of whether our protocol can extend the feasible range of parameters in terms of database size, and also to identify if there are certain parameter ranges where our solution is faster than all known constructions of 2- or 3-party ORAM protocols. Finally, I'll note that in a survey of existing ORAM solutions, various protocols do better depending on the different parameters of network constraints, the size of the database, the size of the values that are read and written to. It would be interesting to identify exactly which protocols are superior in which settings and build an end-to-end solution that can appropriately select the right ORAM background for a given user's needs. Thank you.